A couple minutes early, so if anybody wanted to make it to Suljo's talk, we want to give him a couple minutes to get in. Suljo's going to set up the computer.
He's going
to be too long, so we're not going to wait too long. But I don't think John introduced us. So the session introduced our first speaker this morning was John Kitchen. He's in the Department of Chemical Engineering at Carnegie Mellon. And my name is Mike Janik. I'm in the Department of Chemical Engineering at Penn State University. Our next speaker who's going to talk will be Suljo Linic. Suljo is a professor of chemical engineering at the University of Michigan. I'm sure he would like every moment given to him. We're only about a minute and a half ahead of time. So if everybody wants to take their seats, we're going to go ahead and start up. You're welcome to use the lapel mic if you'd like.
That's okay. I'll try to do it without microphone. I hope everybody can hear me. So I'm afraid you'll have to carry me off the stage today because I might be a little bit too long because I thought the talks were longer than they are.
We'll carry you. Don't worry.
So I'm going to talk today about some ongoing work in my research group. We've been trying to measure the electronic structure of alloy materials and relate this electronic structure to their catalytic performance. The work is performed by a number of graduate students in my research group, Miranda Nicola, Neil Schweitzer, Ang Liang Xin, and I would also like to note that Miranda is co-advised with Professor Johanna Schwann in my department, and Neil is co-advised by Professor Levi Thompson in my department. So the motivation for this work really comes from a very simple observations that when two metals are brought in contact with each other to form an alloy, they often exhibit a catalytic and chemical and catalytic behavior that's significantly different than simple averaging between the metals or the superposition of the performance of these metals. So clearly there's an electronic communication between the elements in an alloy that is driving this change and that's causing this alloy to be significantly different. So the idea was to really try to develop a simple predictive theory that's going to allow us to relate the composition of the catalytic material to their chemical and catalytic performance. And I will emphasize today that we've been able to do this by simply invoking electronic structure and relating the composition to electronic structure and then electronic structure to catalytic performance. I'm going to discuss this in the context of platinum and nickel alloys, but I would argue that very similar principle can describe any combination of metals of transition and noble metals. So I'm going to first start by really showing you just a couple experimental observations that we made and published in a couple of different articles where we demonstrated that geometrically identical sites on pure nickel particles and on thin nickel particles behave significantly different. So if we create thin nickel surface alloy, we find that nickel sites in thin nickel surface alloy are chemically less active than nickel sites in pure monometallic nickel material. We have established it for the activation of CH bonds in methane. We have also shown that the absorption energy of various adsorbates is lower in these nickel sites of the alloy as compared to the same nickel sites of the pure monometallic nickel. And it's actually illustrated here where we have done density functional theory calculations, basically calculating the absorption energy of various adsorbates on pure nickel, and then comparing this absorption energy to the absorption energy of these adsorbates on thin nickel surface alloy. This is the model of thin nickel surface alloy. The blue is the nickel, and this red is tin. And by comparing this, we see that the absorption energy of these adsorbates is less exothermic on identical nickel sites in the case of thin nickel as compared to pure monometallic nickel. And the question is, what is driving this change? In order to answer this question, we went back to literature and also did some work on our own, trying to understand how an energy of an adsorbate change when we move from this adsorbate and create a simple alloy. And you can show by just looking at density functional theory methodology or any kind of quantum chemistry methodology that really the main source of the change in the absorption energy of this adsorbate is going to be due to the change in one electron energy spectrum and due to the change in the electrostatic energy. Now it can be shown that for alloys this electrostatic contribution is very small, so the main source of change is due to the fact that you are changing one electron energy spectrum. Now this one electron energy spectrum has kind of two different components. One is the interaction of substrate with s and p electrons, and the other one is interaction of substrates with d electrons. And one can show that since s and p electronic band is very similar for various transition and noble metals, then the contribution of these s and p electrons is very similar in different metals. So you're left with just the contribution due to the interaction of the d band, of d orbitals of the substrate, with the interaction of the state of these absorbents. So this kind of thinking has led to the development of a d band theory by Jens Norskov and his colleagues in Denmark. And d band theory states that chemical activity, where by chemical activity I mean absorption energy of various adsorbents in a particular metal, is linearly or is correlated with the center of the d band. So the higher the center of the d band I have for a given geometry, I'm going to have a higher absorption energy. And this is nicely illustrated in the case of absorption of CO on various sites on platinum and some other metals here. Now, this d band theory is actually predictive when it comes to pure metals. So if you give me a metal, I can tell you what the position of the d band center for that metal is with respect to some other metal, and therefore I can tell you how various adsorbates are going to bind to that particular metal. So if you learn that basically d band center moves up in energy as we move in this direction in the periodic table, simply because you're changing filling of d band, and also it goes up in energy as we move up in the periodic table, and this has to do with the spatial extent of d orbitals. So now it's simple to predict this in pure metals because simply we know what the filling is. We know that silver is going to have 10 d electrons, palladium is going to have 9, and so on. When it comes to alloys, it's not clear what the filling is because there can be a charge transfer between elements in an alloy, and it's also not clear how the geometric structure of the band affects the position of the d band center. So when one thinks about how would d band center get affected when you form an alloy, there's a number of mechanisms that one can think of. So if I go and I create an alloy, a d band center can shift for a particular site on this system, can shift if I have a charge transfer from one element on an alloy to another element. And if this d band is still the same as in the case of pure metal. So basically I would have a charge transfer within this rigid band framework that would cause my d band to shift. So in this case, the position of the center of the d band, and therefore the change in the absorption energy, would solely be a function of the filling of the d band, which depends on the interaction of the metals that are forming an alloy. And another scenario is basically to have a significant restructuring within the d band without any charge transfer. And in this case, the position of the center of the d band would be simply a function of the width of the d band. So if I, as a consequence of alloying, change the width of the d band, even if I keep my charge on a particular atom in an alloy the same as it's in the case of pure metal, my d band is going to shift and my chemical activity is going to be affected. The third case is really to have a combination of these two, which is really even more complex and makes this problem very difficult to track. So we decided to ask the question, why does Sn lower the chemical activity of nickel sites? And in order to answer this question, we really wanted to measure the width of the d band localized on nickel atoms in Sn nickel and in pure nickel, and also the filling of the d band localized on nickel atoms in Sn nickel and in pure nickel. So in order to do these measurements, we use electron energy loss near Earth spectroscopy to measure the states above the Fermi level, and we use OJ electron spectroscopy to measure the states below the Fermi level. Before I show you results, let me just illustrate here what this electron energy loss near Earth spectroscopy does. So basically, you have a specimen here, basically a catalytic particle. You send an electron beam to this catalytic particle. These electrons are interacting with 4 states of these atoms in this particular particle, basically ejecting the electrons from 4 states into the states just above the Fermi level. The electrons that are transmitted to the specimen are losing the energy, and you're basically getting a fingerprint of the electronic structure localized on a particular atom just above the Fermi level. So in this case, we are looking for the local density of states projected of nickel atoms just above the Fermi level. And this is the result. And I would point your attention only to this panel here. These other ones are just to support the argument that I'm making. So what we see is that when we create thin nickel surface alloy and compare the electronic structure localized on nickel just above the Fermi level, we see that in the case of thin nickel, we have a significant broadening of the d states above the Fermi level as compared to pure metallic nickel. Now, if we integrate area under this curve here, that is informing us about the number of states localized on nickel just above the Fermi level, basically the number of d holes. When we do the integral for nickel and Sn nickel, we see that the number of states localized on nickel is preserved. So you basically, what I see is that formation of thin nickel surface alloy leads to the broadening of the d states of nickel. However, there's no charge transfer or transfer of these d holes in the process. We can also ask the question, what causes this broadening of the d band to take place? And in order to this, we have performed density functional theory calculations looking at the states above the Fermi level localized on nickel. And what we see is that the d band associated with nickel for SN nickel is broadened because you simply form chemical bonds between SN, SP states of SN and D states of nickel. So you have hybridization, you create new orbitals, and these new orbitals are now spreading your band. We can also look at the states below the Fermi level using Auger electron spectroscopy, and the story is the same. Again, in the case of SN nickel, you see broadening of the band below the Fermi level as compared to pure monometallic nickel. If you do quantitative analysis of this spectra, you conclude that there is no electronic charge transfer from SN to nickel or from nickel to SN. So this led us to postulate a simple model, which we call flexible band charge neutrality model, which says that when alloy is formed, there's a change in the structure of the d band. However, this change is not accompanied by the significant charge transfer from one element in an alloy to another element in an alloy. So this is the picture that I want to use to explain this. So basically, if I have a d band of nickel that looks like this red color here, if I form SN nickel alloy, the d band of nickel changes so that there's more states appearing above the Fermi level, more states appearing below the Fermi level. However, the integral under the curve above and below the Fermi level stays the same because the charge is basically preserved. So effectively, the center of the d band shifts down in energy. As the center of the d band shifts down in energy, that's telling me that I have d electrons now, nickel d electrons associated with this SN nickel that are less energetic than in the case of pure monometallic nickel, and these electrons are now interacting with adsorbates in a way that these adsorbates are binding less strongly to the identical geometric site in SN nickel as compared to pure monometallic nickel. And the reason is when you have an adsorbate, when you interact this adsorbate with these d states, bonding and anti-bonding states are formed. These anti-bonding states basically sink down below the Fermi level, and you have more electrons in the anti-bonding state, you weaken the bond. So this was observation that we made for nickel, and we also did similar studies for AG nickel and AU nickel with the same story. However, the question is whether this is a universal observation. So in order to answer this question, we moved to a family of platinum alloys, and we mainly studied SN platinum alloy and also various combinations of 3D metals and platinum. These combinations of 3D metals and platinum, actually, these are very good electrocatalysts from low temperature fuel cells. And the reason why they're good is because they bind adsorbates less strongly. So in the case of CO poisoning, platinum sites associated with an alloy that has 3D metal and platinum bind CO less strongly, so CO poisoning is less of a problem. They also bind oxygen and OH adsorbates less strongly, which then causes oxygen reduction reaction to have a lower order potential loss for platinum sites associated with this 3D metal platinum alloy compared to the pure platinum. So again, you're kind of in a strange situation because you have a 3D metal which is usually more chemically active than platinum, basically lowering the chemical activity of platinum itself. So you're creating new sites which are chemically less active than the sites associated with pure platinum and the sites associated with 3D metal itself. So now in order to probe the electronic structure of platinum, we use XANES, near-edge spectroscopy, and in order to establish alloying, we use XARCs and XRD. And I'm just going to show XARC results for the case of SN platinum alloy, but we have obtained similar results for copper platinum, ruthenium platinum, molybdenum platinum, and so on. And what you see here in the case of SN nickel is that when you look at XANES spectra, the spectra changes significantly as you form SN nickel, and we can fit this new spectra of SN nickel very nicely. The fit is in red, and the dark is actually SN platinum alloy, and we can fit this using this alloy structure that I have here, the unit cell. Here you see the fit is very good in real space and in phase space. You can also use XRD to establish alloying, and you can see clearly that the XRD of pure platinum particles and of these SN nickel platinum particles are significantly different from each other. Now, if we look at near-edge region, just the states above the Fermi level localized in platinum, we see that there's also changes that are taking place as we form these alloys. So these changes are manifested in the either broadening or narrowing of the D band, and the onset of this edge also moves a little bit depending on what alloy we are dealing with. If we integrate under this curve, we again are getting the number of states localized with platinum just above the Fermi level, and irrespective of what alloy we are dealing with, we get the number of these states localized in platinum is So basically the story is the same for platinum alloys, a number of these alloys, and that twin nickel and nickel alloys that I've discussed before. So basically the filling in the platinum D band is preserved. Local electronic structure does change because you create bonds between platinum and these impurity elements that are used to form an alloy, and the center of the D band now has to shift to accommodate these changes. So now this leads me to a very, very simple model that can basically tell us how the position of the D band center shifts as we form alloys. So what we have concluded is that the change in the width of the D band without the charge transfer drives the shift in the D band center. So the only parameter that matters is really the width of the D band, since all these metals in these alloys are charge neutral because there's no significant charge transfer between the metals. So the width of the D band now dictates what the position of the D band center should be, and the position of the D band center then in fact dictates what the absorption energy of various absorbed. The practical consequence of this is that the change in the D band width can be easily predicted based on just a simple tabulated values or even like a tight bonding approximations and so on. And we have done this here. So basically the width of the D band, if you have this constraint of no charge transfer that I talked about, is basically a function of the extent of D orbitals for a given geometry. So if I have an elongated in space D orbitals, these D orbitals are going to interact, for example, with platinum orbitals, and they're going to make a broader D band, and then the position of the center of the D band associated with platinum is going to be lower in energy. So this is actually illustrated here. So if you go from copper to platinum, here I'm talking about these skin structures where I basically perform density functional theory calculations where we go from pure platinum to form these skin structures in which we take the second layer of platinum, and instead of platinum we put 3D metal. And if you see that there's a nice relationship between absorption energy, hydrogen in this case, and the extent of D orbitals only. And this extent of D orbitals is a tabulated value that you can find in many material science books. And what we see is that in the case of copper, the D orbitals are less extended in space. So that yields a D band center that's basically higher in energy, higher absorption energy for hydrogen. In the case of iron, for example, D orbitals more expanded in space. You end up at the center of D band, which is lower in energy, which in fact results in lower absorption energy for hydrogen. So you can very simply, using very simple theory, predict what the changes should be. And this simple theory applies for not only hydrogen, but also for carbon, CH, oxygen, CO, and so on. Many other absorbers that we have tried. So you get a very, very nice agreement between this extent of the D orbital and the position of the center of the D band. I failed to mention, but I should have mentioned, is that these kind of relationships have actually been anticipated before based on density functional theory calculations by actually John Kitchen, Jens Norskov, Jingwon Chen, and Mark Berthaud published a paper in TRL and Journal of Chemical Physics not too long ago, basically outlining this idea of how the D band center width is a function of the relationship between the center of the D band, the width of the D band, and this geometric extent of the D orbit. So basically, I wanna conclude by arguing that this flexible bond charge neutrality model, which assumes that there is no charge transfer in the process between elements in the process of the formation of alloy, but actually the formation of new states as a consequence of alloying drives the change in the D band, which in fact drives the change in the position of the D band center and the change in the chemical activity of a particular site in an alloy. I would argue that this mechanism might be important for alloys in general. Simple reason is that local potential in metal and screening processes will force this charge neutrality argument to be met. With this, I'm going to finish, and I'd just like to thank DOE and NSF for funding DuPont Camille Drive Future Scholar Program. Again, I'd like to thank Rand and Nicola who performed the work on nickel. Neil Schweitzer and Hans Sin have helped with platinum work. Jeffrey Miller for helping us with zinc studies. And also, as I said before, Johannes Schronk and Levi Thompson were my collaborators in the project. Thanks.
We have time for some questions. I'll start with the first. Well, you can have the first one.
My question is about the composition of the alloys. That you, in your analysis, which is very, very nice, you assume that you have just one composition, but in general, when you have a supported catalyst, you have a variety of, from pure platinum to pure tin and everything in the middle. How do you handle that?
So I mean, at this point, what we were just interested in how the chemical activity and therefore the catalytic performance for a particular site changes as you go from a pure metal to an alloy, assuming that you have a given geometric structure of that particular site. So we didn't take into account all the changes in a catalytic particle being pure platinum and then another particle being some sort of combination of tin and so on. And platinum and so on. Is that the question you're asking?
Well, what I'm saying is that you may have a small fraction of the particles that are only platinum, and they may dominate the whole spectrum.
In you mean the catalytic activity spectrum?
Right.
Yeah, that can happen, but I didn't argue that. I mean, I'm just saying if you can create an alloy, we can predict how the chemistry of that alloy is going to change just by looking at what the composition of that alloy is.
Actually, I have a question about nanoparticles, and if you have, for example, eggshell size or just homogeneously distributed.
Those are all important factors, but again, what I'm trying to tie is really the local geometry to chemical activity. So assuming that I know what the local geometry is, then I can say what the chemical activity should be. And again, tying the width of the band to the center of the D band and to this geometric factor T and the extent of the D orbitals. That would allow us to do it. So I agree with you. If you have different particles, you're going to have different active sites. But if you tell me what the active site is, then I should be able to tell you what the activity of that site is with respect to some other site. We have one more question. No?
So kind of related to this, maybe it's a semantic thing, but so when we talk about D-bands, it kind of suggests a delocalized picture of the bonding, whereas the absorption bonding interaction is actually fairly local. So when you calculate the D-band, is it really the states right at those metal atoms that are involved in the bonding that are important? And would it be as appropriate to talk about the center of the D states at that absorption site as it would be to the center of the D-band, which...
Right. So what I've talked about here is mainly the local density of states projected in a particular atom. So D center projected in a particular active site.
So
That's
these
what
are
I-
not the center of the D-band of the entire material, it's the D-band at the site
Right.
at which the absorption is
That's
happening.
exactly it. Because if you have the entire material, one element is going to have a different electronic structure, local structure than compared to.
So it really is a local
Right.
effect that's just expressed
Right.
in terms of the D states at those local.
Finally, we've answered that question.
What's that?
Finally, we've answered that question for you.
Let's not call it a band, let's call it a core.
All right.
I the same thing.
Do you want to grab your line?
You say tomato, I say tomato.
That's right. All right, we are perfectly on schedule. Thanks for everybody's work on that so far. Our next speaker is going to tell us about the first principle studies of surface oxide formation at electrode surfaces.
Good morning, everyone. Today I will talk about the first principle studies of surface oxide formation on platinum electrodes. So here is the outline of my talk. First, I will give some brief introduction on the background and my study purpose, and then a brief introduction of the study method I use in this talk. The main part of my talk will talk about the results of oxide formation on 3 different kinds of platinum surfaces, and then finally it comes to a conclusion. So why we want to study the platinum oxide formation? Because first, it's related to the stability of platinum electrodes. We know that when we increase